Okay, this is chapter 4, and in chapter 4, it's a little different from chapter 3. In chapter 3, we looked at quadratic functions, and quadratic functions can be written in the form, just a sec, f of x equals ax squared plus bx plus c. Okay, and that's just a standard form. Okay, and you know that they can also be written in the vertex form, but that's an example of a quadratic function. Now, quadratic equation is just a little bit different. Okay, you know, quadratic function, you can graph it that f of x or y will always change with when the x changes. A quadratic equation is when you have ax squared plus bx plus c, and that equals 0. Okay, so just a little bit different. So just to make that distinction for you, so when we say we're focusing on describing the relationships between the roots of a quadratic equation, okay, and I don't know if you've found roots before, maybe when you were factoring quadratic equations, the zeros of the corresponding quadratic function, so that would be when you have your quadratic function and you graph that nice parabola, okay, just like that. The zeros would be where does y equal 0, right? So essentially, where does it cross the x-axis? And the x-intercepts of the graph of the quadratic function. Okay, so the zeros when you're just thinking of it as a function, or the x-intercepts when you're actually considering the graph. And then we look at how we would solve the quadratic equation by graphing the corresponding quadratic function. I kind of give you a little bit of that right there when I drew um, that diagram right there, just to show you that if you wanted to know what how to solve the quadratic equation that was represented by that, you can graph the function and find out where those zeros are. Okay, so that's basically the difference between 3 and 4. So you have an example here, just a quick example where it says they show you a picture of a water fountain, and so for each of those each of the jets that comes out, it comes out in an arc that's basically a parabola, and the jets are designed to land precisely on the underwater spotlights. Okay, so they just set it up so that uh, wherever the water's going to land, that's where they're going to have a jet, right there. Okay, so that's where they're going to have a light. Okay, so it just makes it a little nicer. So each water fountain jet creates a parabolic stream of water. You can represent this curve by the quadratic function h of x equals negative 6 times x minus 1 squared plus 6, where h is the height of the water and x is the horizontal distance of the jet of water from the nozzle, both in meters. Okay, so it gives us a quadratic function. We can graph that quadratic function. They've done that for us, and then we want to find out where that distance is, where the light has to be. And actually, they haven't really done it for us. They've just kind of showed us a sketch. So we need to actually make a real graph of that function. Okay, so I'm going to go to Excel, and I'm going to use, I'm just going to type in that formula. So here's where my x values are going to be in this first column. My h values are going to be in the second column. Anytime I want to calculate my h value by saying negative 6. You probably have to put multiplication signs in here. You can't just put the brackets. So negative 6 times, and then wherever my x is going to be in cell A2, so I'm going to put A2 instead of the x, minus 1, close the brackets, to the power of 2, okay, and add 6 to that, okay, and then so for whatever I put in that x value, it's going to calculate it, okay, it's going to calculate it in the next column, okay, so maybe I'll go up by 1, we'll see how that works. It doesn't, you can just test it out, you can try and see if the increment that you've chosen really works for it, so A2 plus 1, and we'll just make a few more, and I mean I'll be able to see whether I've chosen a good value by how much I'm going up by what happens with my y or my h values. Okay, so just copying here. So I go copy, paste it on here. Yeah, so I can see that maybe I didn't choose the best, okay, although I can see that it's 2 meters away, right, because it starts at 0 and it comes back at 0. But to get a better idea of, you know, the curvature of it, I think I should maybe go up by, maybe I'll go up by 0.25, okay. And then it'll just give me a better graph. And I don't actually need any values that are less than 0, so I can just even get rid of these ones. Okay, and then again we highlight, insert, scatter plot, just need the lines, and it looks like that. Okay, so that tells us, and so here's what it says: investigate solving quadratic equations by graphing. So by doing the graph of that, I can look at it, I can see that the peak height is 1 meter away, okay, and I can see that it hits the ground again 2 meters away. So that tells me that um, each of the underwater lights should be placed 2 meters away from the center. The second part of the question here says that you can control the height and horizontal distance of the jet of water by changing the water pressure. So suppose that the quadratic function h of x equals negative x squared plus 12x models the path of a jet of water at maximum pressure, and the quadratic function h of x equals negative 3x squared plus 12x models the path of the same jet at lower pressure. You want to graph these two functions on the same set of axes as in step 1 and see what you notice about the x-intercepts and height. Okay, so I did that over here on Excel. I'll just point something out to you. I don't know why this happened, but it wasn't working properly when I tried to graph that one, and I just put a negative sign, negative a2 squared, so I had to put a negative 1. So I put that a value of negative 1 in, and then it all worked well. Okay, so if we graph all three of these, you're going to end up with a slightly different chart. You'll notice you have a lot more points for the ones with a negative 1 as the a value, which makes sense because you know that's going to be a much wider graph. Okay, it's actually going to be 6 times wider, right? Because you have an a value of 6 in the first one, and then this one has an a value of 1. Okay, so if I insert a chart for that, again, the scatter plot, we just want to see the lines. Okay, you're going to end up with this. Okay, so the first one, the blue one is the first one that we did, and the green one is the next one. Okay, we're getting a little wider instead of having an a value of x, we're having an a value of 3. Okay, and then or an a value of 6. Okay, and then we have our other function, negative x squared plus 12x. Okay, so looking back at our question, we'll describe what you notice about the x-intercepts and the height of the two graphs compared to the graph in step 1. Okay, so again, the graph in step 1, that's the blue one, and we notice that the other two have higher height, and they also have larger x-intercepts. So the one is still at 0, but the graph, because the graphs are wider, you're going to have your x-intercepts be further apart. And the other thing that they ask, why do you think the x-intercepts of the graph are called the zeros of the function? Well, you can obtain those x-intercepts by setting the value of the function, or the value of y, to 0. Because looking at those graphs, you have the x-intercept when y is equal to 0. Okay, number 3, if the water pressure in the fountain must remain constant, how else could you control the path of the jets of water? You could do that by changing the angle that you shoot the water out at. That would make it go further or go higher, depending which way you chose to alter the angle. Could two jets of water at constant water pressure with different parabolic paths land at the same spot? Explain your reasoning. Constant water pressure being the same for both. It would have to be, could be constant water pressure, but the two jets would have different water pressures, so that if one had a lower water pressure, it could you could choose to angle it more toward the horizontal, okay, make it go further, and if it had a higher water pressure, you could choose to angle it more toward the vertical so that it would go higher and then land on that same spot. Okay, so just to summarize there, quadratic equation is in the form ax squared plus bx plus c equals 0. Okay, so instead of having f of x, you've got the 0. The roots of an equation are the solution, so once you set it equal to the 0, what would be the values of x that would make that true? And the zeros of a function are where you set f of x equal to 0 and find out what the x value would have to be to make that happen. You can solve a quadratic equation of the form ax squared plus bx plus c by graphing the corresponding quadratic function. So that's what we did there. Okay, we saw where it crossed the x-axis. That gave us the roots of the equation, or the zeros of the quadratic function. Okay, and so Just one method, graphing and then looking at where your x-intercepts are.